Hi, I'm Metta Spencer. We're going to Columbia University today, and we're going to meet a geochemist with a woman I'm just getting acquainted with. This is Claire Nelson, who is at her home in New York City with a Christmas stocking behind her. Hello, Claire. How are you?
Hi. I'm good. Thank you for having me.
It's fun. I'm really looking forward to this because you have answers to questions that have been really bugging me. Because I am interested in climate change. Everybody should be. And I'm trying to get smart about how it all works and what we can do. Some of the things that I think need to be done not instead of, but on top of, in addition to reducing emissions of carbon to the atmosphere, I think we have to take carbon out of the atmosphere and put it away. And so I've been looking at all of the zero emissions or negative emissions technologies that I can get hold of. But as a non-scientist, I sometimes find myself at a loss. So I want to learn from you, if you will, about basalt weathering or basalt mineralization, which I got this far. I know basalt is some sort of volcanic rock. It's very, very common, isn't it? Maybe the most common kind of rock in the world. Is that right?
Yes, if you include the ocean floor, then yes.
Oh, okay, good. And so we want to understand how that can take in carbon out of the atmosphere. So why don't you start at the top and explain the basics?
So most people, when they learn about the carbon cycle or think about the carbon cycle, we think about photosynthesis, right? We learn this in elementary school. Trees take in carbon and they release oxygen. But there's this other carbon cycle that's actually way more important that most people don't know about unless you take a geology class. And that's called the long-term carbon cycle or the geologic carbon cycle, which has nothing to do with plants, nothing to do with biomass. And it just refers to transfers of carbon between what are called inorganic reservoirs, so no plants. And if you're familiar at all with Earth history or geology, the Earth is billions of years old. And for the first 2/3 of the Earth's existence, there were no plants, but there still was a carbon cycle. And that carbon cycle is what's responsible for controlling global climate over long time scales. So it's really the permanent carbon cycle. And so that's what I studied in my PhD at Northwestern. So I'll explain it to you as simply as I can. But basically, volcanoes emit CO2, and that CO2 hangs out in the atmosphere and controls climate via the greenhouse effect, which hopefully we're familiar with. And the thing that actually removes that carbon permanently, yes, plants do remove it, but not permanently. They die after 40 to 100 years. The actual only permanent sink of carbon is what's called the silicate weathering carbonate precipitation cycle, which I'll just refer to as natural mineralization because that's just easier and makes more sense in the context of carbon capture. So this process that I call natural mineralization has two parts. You need to get the CO2 from the air as a gas into a rock. And the first part of that is converting the CO2 to dissolved form. And that's what's called chemical weathering. So certain types of rocks like basalt, they actually dissolve and erode slowly over time. And that chemical reaction of a rock dissolving consumes CO2. It sequesters CO2 from a gas in the atmosphere and actually dissolves it into rivers. So kind of a similar-ish way to think about chemical weathering is like rust. Like it's a chemical reaction between a metal and atmospheric gases that results in the metal kind of dissolving. So you see rusty things that have holes. So a similar concept applies to rocks on Earth. Like a lot of the fancy screensavers that we see and beautiful geologic formations around Earth all happened because rocks dissolved in a cool way. So it's kind of counterintuitive to think about rocks dissolving, but they do. And that chemical reaction is extremely important because it pulls down CO2 and puts it into water. So that's part one, is chemical weathering, removing CO2 from the air, putting it into water. So what happens to that CO2? It eventually flows through rivers and goes into the ocean. And a long time later, about 1 million years, the CO2 and different metals that come out of the rocks, like calcium or magnesium, combine in oceans during what's called carbonate precipitation. So this is the mineralization part, because you're turning carbon into a mineral or a rock. And it's a little bit more easy, accessible to think about this, because shells or corals or limestone is all forms of calcium carbonate or carbonate minerals. So all of the carbon that is in a shell, for example, was once in the atmosphere. So there's a lot of different ways this can happen. Like a shell or a coral, for example, is assisted by biology, but it also just happens without biology during carbonate precipitation. So those two things, calcium and carbon, just smush back together and form a rock at the bottom of the ocean. And then eventually the ocean floor gets subducted under a plate during tectonic activity, and that carbon is recycled back into the mantle and released again during volcanoes. So that is the actual long-term carbon cycle. And it's permanent because it's like, as soon as you precipitate carbonate at the bottom of the ocean, it gets buried there for millions and millions of years. So permanence and timescales are always relative. So for example, nothing in geology is technically permanent, but that is the permanent, the longest term sink of carbon. So that process is what controls global climate over long, long time scales. And so it's an important negative feedback loop, which basically, as you emit more CO2 into the atmosphere through volcanism or whatever, that speeds up the dissolution of rocks, and that speeds up the pulling down of carbon. So it's a negative feedback loop that our Earth has figured out in order to stabilize climate. So it's the way that the Earth kind of responds to perturbations in the carbon cycle. And I'm not talking about human-caused climate change perturbations, because that's on such a short time scale. We're emitting CO2 so rapidly that the chemical weathering response that will kick in and pull it down is going to lag by about thousands to tens of thousands of years. So basically, we need to figure out how to speed this up to help us out. And there's multiple ways that is done, but I'll talk about that in a second. First, I'll just tell you a little bit about my PhD research in Iceland. So I mentioned that certain types of rocks chemically weather. It's not all rocks participate in the regulation of climate. Certain rocks are better than others at pulling down CO2. And one of those types of rocks is basalt. It's suggested to have a disproportionate role in the regulation of climate, naturally speaking. And some estimates point that to the basalt consuming about 30 to 35% of all CO2 that's drawn down today by this chemical weathering process, despite the fact that basalts only comprise 5% of the continentally exposed area. So big disproportionate role. And there's two reasons why basalt matters a lot more than other rock types. The first is that it's really rich in those metals like calcium and magnesium and iron that are specifically needed for the second part of natural mineralization. You need one of those three types of things to bond with carbon. Not just anything will precipitate with carbon. You specifically need calcium, magnesium, or iron. So basalt has a lot of minerals rich in those things. And the second reason is that basalt is thought to dissolve a lot faster than other types of rocks. It's very reactive. So it dissolves faster and thus pulls down more CO2 than other types of rocks like granite, for example. So my PhD research, I was kind of testing a lot of the underlying assumptions that go into the collective agreed upon knowledge in the geochemistry world that basalts play such a disproportionate role. I was interested particularly in like, how much is that actually true? And what are the parameters that can speed up the natural weathering rates of basalt? So I went to Iceland and collected river samples, and because rivers like contain all this stuff that is released during the chemical weathering. So when a rock dissolves and pulls down CO2, it goes into a river. So rivers offer essentially a snapshot view into the long-term carbon cycle and help us quantify how much is Iceland naturally drawing down CO2 today. So you can figure that out by looking at the chemistry of the rivers.
Did you find out what you thought you were going to find? And were you pleased at how much it's doing?
So a lot of, basically we found what we thought, but what we thought wasn't, we meaning my group at Northwestern, but what we thought wasn't necessarily what the assumptions had pointed towards for the past several decades. So essentially, we used a new tool called calcium isotopes, which are just a fancier thing to measure. In the past, people would just go scoop up some river water and look at just how much carbon is in there, like what's that number, just carbonate concentration, and make the assumption that all of that carbon has come from the atmosphere when it's pulled down during weathering. But there's also other sources of carbon to rivers, like the weathering of carbonate minerals, like different types of minerals. So the minerals that I mentioned that form in the ocean, the calcium plus carbon, those also form in volcanic settings, just like in like hot springs. Sometimes you'll see like a white crust over a hot spring that's just calcium plus carbon. And the good news is that mineral is very what's called thermodynamically stable, meaning it likes to form at the surface Earth. Those two things want to be together, which is good for us in terms of the geoengineering side. But it just means that that mineral is very common, especially in places that are kind of hydrothermally active, like Iceland.
What is it? Limestone or what?
It's
the product.
Calcite.
Calcite.
Yeah.
Okay.
So there's that's pretty.
You've seen bubbly stone-like things at geysers. Is that right? Is that what you're referring to?
Yeah, just sometimes like even sometimes like in your house, in your shower, there's like there can be like a white crust around your shower head or in like the bottom of your kettle when you like make tea. Like that's very common that mineral forms, because anytime that there's calcium and carbon present together in water, the mineral usually, not always, sometimes forms. So essentially that mineral forms naturally in Iceland, just as a byproduct of the weathering process. So that mineral, this kind of might be getting too sciencey, but basically that mineral also dissolves and weathers sometimes, and that releases carbon into rivers that is not from the atmosphere. It's from the mineral. Mm-hmm. So essentially there's, long story short, you can't just assume that all the carbon in rivers is from the atmosphere. It can come from mineral reservoirs of carbon, or it can come from volcanic degassing. So we basically needed a better way to differentiate where the carbon and the calcium was coming from to these Icelandic rivers in order to quantify carbon drawdown. And that's what my PhD research was, is using a new specialized tool, isotopic tool, which just means nothing to most people, but it's essentially just a new way that we figured out to trace this and to better constrain, okay, how much of the stuff in these rivers is actually from the weathering of basalt and carbon drawn down from the atmosphere, trying to like correct out other sources.
Tell me the whole cycle again. It's because
Yeah.
it's absolutely new to me. You know, I never thought of it as a cycle.
CO2 is in the atmosphere, and
well, it comes from the volcanoes, right?
Yeah.
Yeah, that's the interesting thing, because I had never heard that part before. Volcanoes are not nice. If they'd stop, then we'd be better off. Is that right?
Yeah. Well, we should stop first, but yeah.
Oh, yes. Okay. Got it. Go on.
Yeah.
Now, so they come out, the CO2 in the is in the atmosphere. Now, that step 2.
So CO2, during chemical weathering, which is when rocks react with the atmosphere, that process dissolves not only the rock, which releases calcium and stuff into rivers.
But to get it into the rock, how does the CO2 get into the rock?
It goes into the water first. So I think I
might have like into rain or something.
Yes.
So, and then it hits the stone and gets absorbed into the stone. Is that the way when it's mineralizing? That's the phase of which no,
it goes into it rivers first, so it becomes a dissolved CO2. So it might help. Yeah, if I back up a little bit and say that like CO2 and water vapor in the atmosphere, they're both in the atmosphere. And then when it rains, you're pulling down little bits of CO2 in rainwater, and rainwater is slightly acidic. With what's called carbonic acid. So carbon dioxide can act as an acid. So like, for example, when you drink soda water has like a pH of like 4. It's very acidic because CO2 gas plus water makes carbonic acid. So it's slightly acidic. But that when that acid-ish soda water rains down and hits a chunk of rock exposed at the surface, that acid dissolves the rock, and that converts carbonic acid to what's called bicarbonate. So it's still carbon in water, but it's a different form. You're chemically converting it from a gas to a dissolved form. Mm-hmm. So this kind of gets like into more geochemistry, but it's a kind of a simple like acid-base reaction that we learn about in like high school chemistry. But if they had taught high school chemistry through the lens of the carbon cycle, I think more of us would probably remember because it's more tangible. But essentially, so that part is basically sequestering CO2 into a dissolved form. And then that carbon in rivers flows out into the ocean and eventually recombines with calcium. So that is the overarching long-term carbon cycle.
So the bicarbonate or something is in the water, and then it combines with calcium and becomes like a shell, only it's a rock.
Limestone. Yeah.
That's limestone. Is
yes.
that limestone? Okay. Shells and stuff are limestone. Okay.
Yeah.
And then it goes to the bottom of the ocean, and then what happens?
And then it stays there for millions of years and eventually is tectonically recycled back into the earth, and that carbon gets re-emitted as volcanoes. So that's the climate controlling system that the earth has figured out.
It's there's something inspiring about the notion of all of these enormous plans. it's really, you know, almost if you're religious, you can be overwhelmed with the beauty of the system. Thank you. Okay. Now then, what does that have to do with how we're going to take carbon out of the atmosphere and sequester it beyond what plants and animals can do, or plants can do for us?
Yes, so this is the exciting part. But I just wanted to at first like back up to something you said earlier on about how like why we need carbon capture to combat climate change. So essentially like the IPCC report in 2018, which I'm sure you're familiar with, basically published this report saying that in order to meet the goals of the Paris Climate Agreement, we need to not only stop emitting CO2 like today, but we also need to sequester and consume about 10 gigatons of carbon per year to curb global warming under 1.5 degrees C. So 10 gigatons, it's hard to think about these like numbers, but basically that's 10 billion tons. So that is the bare minimum that we need to be sequestering and capturing if we stop emitting.
And if we do better than that, maybe we'll get to straighten ourselves out pretty quick.
Yes. So that 10 gigatons per year number is removing what's called the legacy carbon. So the carbon that's already damaging the earth, that's been emitted to the atmosphere for the past however many years. So not only do we need to stop adding carbon, we need to also remove the legacy carbon that's already in there. So carbon capture and storage, it's confusing. You could think of maybe a Venn diagram. Carbon capture and storage can help with climate change mitigation in both two ways. One is to help us get to a zero emissions world by capturing and storing the carbon that is being emitted through the burning of fossil fuels. We can also use it as a negative emissions technology, which is basically a technology that can pull emissions down and remove that legacy carbon once we hopefully get to a zero emissions world. So you hear a lot of these phrases like net zero and all that, but it's not good enough to just capture and store all the carbon that we're emitting or offset the carbon that we're emitting with carbon capture. We have to use carbon capture as a tool to get to a decarbonized world.
Yeah, but you said something that bothers me a little when you said once we get to net zero. Well, we can't wait till we get to net zero. We have to be doing the sucking it out at the same time as we stop putting it out into the atmosphere, right? So we have to be doing both right now.
Yes, that's right. I exactly agree with that. Yeah. So a lot of
I'm so glad you say that because I am one of my big beefs, and I have more than my share of beefs. But one is that so many people, environmentalists and climate change people, downplay the importance of this negative emission thing, and don't want to talk about it because they say, shh, if you let people think that we could take it out of the atmosphere, they'll go around thinking, well, we can just keep on putting it out. So we don't want them to know that we could actually draw it out because they won't cooperate with our effort to keep them from putting it out there. And that's the logic that drives me crazy.
I hear that a lot as well. And I see the point. A lot of environmentalist groups are of the mindset that we shouldn't even be talking about carbon capture. But unfortunately, the IPCC report made it clear that we still need it to remove legacy carbon. And unfortunately, business will be business and economics will probably drive us to the point where big companies will use carbon capture to offset their emissions as an excuse for them to just pay a price and keep emitting, which is unfortunate. And I don't condone that and want to make it very clear that the scientists working on these problems are very aware of that as a possibility. And I'm also painfully aware of a bunch of startups and industries that are in the carbon capture world that are not really focused at all on climate change mitigation. They're simply trying to profit off of what they believe will be $1 trillion industry. which is really unfortunate. But such is life. That is how people work. So yeah, so in reality, that 10 gigaton per year to remove the legacy carbon, that number needs to be a lot bigger because unfortunately, realistically, we're not in any rush to stop emitting fossil fuels today as a global society. So we do need the carbon capture industry to be much bigger than 10 gigatons per year. So humans emit about 50 billion tons a year, so 50 billion tons. So we need a carbon capture industry that's closer to the size of the current fossil fuel industry. If we're going to get to net zero, even though I don't believe net zero should be the goal, I think zero and negative should be the goal.
How are you going to speed up this process, this cycle that you've talked about, and put more of it away in the stone? So let's go back to Iceland and tell me what they're doing there. What is this CarbFix thing?
The first part is the rock dissolving, and that pulls CO2 from the air into rivers. The second part is in water, the calcium and carbon combine to make a mineral. So that's the two-step part of natural mineralization. So essentially, we can exploit basalt and this natural mineralization process in broadly two pools, I guess. One of them for carbon capture and storage. One of them is what's called enhanced weathering. So that is the first part. You're enhancing the rate at which the silicate minerals in basalt dissolve, because that pulls CO2 out of the air and traps it as a dissolved phase in what's called solubility trapping. So the way that that's being researched currently is by crushing up basaltic rock or certain minerals like olivine and spreading them out over cornfields or over coastal regions. And the idea is that if you crush up the rock, you're exposing a lot more surface area for reactivity. So you're increasing the reactive surface area for it to dissolve and react with CO2. And if you put it in the ocean has a much higher concentration of CO2 than the air. So the idea is that will speed it up faster, and you'll convert carbonic acid into bicarbonate at a much faster rate. And so that is what's called.
It'll work better in the ocean than if you spread it on fields.
I believe so, yes, but we need more field trial data. But yeah,
I've heard you mentioned olivine. In fact, I hope we will shortly do a talk show with some folks in California who want to do things like spread olivine, crushed olivine on beaches.
Yeah,
that's related to what you're saying, right? Mm-hmm.
Exactly, yes. There's a group called Project Vesta. My friend Grace Andrews is the director of scientific operations there. So everything I'm saying basically comes from her. So maybe you can ask more questions to them about this process, but I just wanted to mention it because it is one of the ways that basalt weathering or that silicate weathering is being researched and exploited as a carbon capture and storage mechanism.
But the olivine then is different from basalt, but it's better than basalt at capturing carbon, or not?
Yeah, so olivine is a mineral within basalt. So basalt is a rock, and rocks are just a amalgamation of different minerals. So one of the main minerals in basalt, there's several different minerals, like, I don't know, their names are not that important, but plagioclase, clinopyroxene, and olivine are all minerals that make up basalt. And olivine is particularly important because it dissolves the fastest. It is the most, what we call, thermodynamically unstable at the surface Earth. So different minerals like to form under different pressure, temperature conditions. And as I mentioned earlier, calcite is thermodynamically stable. It likes to form at the surface Earth. Olivine is the opposite. It doesn't like to live at the surface. It's kind of likes to be higher temperature. And so because of that, it likes to dissolve at the surface earth. So it dissolves more quickly and more readily than other types of minerals. So yeah, that's why olivine is particularly important. But basalt is like olivine is very common and there's, you can mine for it, whatever, but basalt is kind of the more like general, probably lower budget option than pure olivine.
I love the way you describe these minerals. It's almost like you're talking about people with specific personalities, and you're talking about their traits and habits and lifestyle.
I do think that way about rocks. Yeah, so that's just the way that I can think about thermodynamics. But
okay.
So yeah, so basically the first way that we use basalts to capture and store carbon is enhanced weathering, and there's a bunch of different types of that: terrestrial, ocean, and you can ask the Project Vesta folks more about that. But what I do is the other part, which is called, well, there's a lot of different names for it, but broadly speaking, mineralization. So, and that is part 1 and 2 of the natural mineralization. So you're taking CO2, first mixing it with water, and then actually reacting it so that you're precipitating or mineralizing calcite or other carbonates. Calcite is just the calcium variety, but I just wanted to be clear in case there's any scientists watching. There's other types of carbonate minerals too. Like, so that is basically CO2 to water, and then the calcium and CO2 to mineral. So part 1 and 2 of what nature does. So you're doing the weathering, you're dissolving basalt or reacting it, and then you're also making a mineral. So it's different than enhanced weathering, which just pulls CO2 down and makes it dissolved by carbonate. You're taking it one step further and making a carbonate mineral. So hence the term mineralization. But there's different, so now we're in the umbrella of mineralization. There's 2 different types, broadly speaking. One of them is what's called ex situ mineralization. So, and then versus ex situ versus in situ, like, and that just refers to okay. Are you using a rock that's a geologic formation where it is, like Iceland, or like the Columbia River basalt, meaning you're bringing the carbon and stuff to the rock? That's in situ. Or ex situ is you're using, for example, mine tailings or like mafic waste that is out of where it formed.
Are you bringing the mountain to Muhammad or Muhammad to the mountain? Right?
Exactly.
Bringing the mountain to what you want to have done.
Yeah.
Versus bringing the chemical to the mountain. Oh, got it. All right.
Yeah. Another way that I think about it, that's easier to think about, which isn't always like, I don't know. So that maybe an easier way to think about it is like, are you doing this at the surface or underground? Like, are you injecting stuff down into basalt, a basaltic formation, or are you using basalt powder at the surface to react and mineralize carbon? So a lot of that, I'll just briefly talk about the ex situ part because I don't know that much about it, to be honest. But essentially, people had observed that a lot of mine tailing waste is basaltic-ish just naturally. So we just happen to have tons of mine tailing piles that are crushed up basalt ready to go, either ready to be used for enhanced weathering or mineralization. And the ex situ mineralization piece comes in because people had just observed naturally that as that pile of basaltic mine waste was out there exposed to the atmosphere, you could actually see little carbonate crusts like forming. So people just realized that nature does this. So now there's some research groups kind of figuring out how we can use mine tailing waste to make more carbonate minerals at the surface. Like, do we stir it? Do we do whatever? So I don't know that much about that, but there's some people trying to figure out how to not only just use that mine tailing waste for enhanced weathering, but also for the mineralization piece, and seeing if you can grow carbonate minerals at the surface earth using this mine tailing stuff.
Well, I've heard people say that you might take the mine tailings and use that to scatter on the cornfields and stuff.
Yeah, that is. Yeah,
that could enriches the soil and it captures carbon, right?
Yes.
So, okay. I don't know how. So that they might be able to just do that. Is anybody doing it yet, as far as you know?
Yes, they are. So I know that, well, field trials of enhanced weathering, Grace Andrews at Project Vesta did the first ones when she was a postdoc at University of Southampton in the UK. They have a big research group doing that there. And also my other friend, Garrett Boudinot, is at Cornell, and they're doing more field trials. And then there's a lot of groups in Canada, University of Calgary, I believe, University of Alberta. I don't really know, but Canadians are all over the mine tailing stuff. So that's great. So yeah. But the second type of mineralization, which I'm obviously biased and I think is the most promising in terms of scalability, is in situ, or like subsurface. So you're actually injecting carbon underground into rocks and reacting it with the basalt and precipitating out carbonate minerals.
Okay, now you're going to take the water that has carbon in it, carbonated water, and you're going to shoot it in the ground.
Yeah, that's one method.
Well, there are others.
So, well, there's only been 2 field trials of this. One of them is in Iceland, where the CarbFix folk over there are scaling up to like commercial scale sites and industrial scale injection sites. And then there was another field trial in it was called the Wallula Basalt Pilot Project out of the Pacific Northwest National Lab in the Columbia River Gorge. So I'll explain the difference between those two. But first, the CarbFix method is they're exactly what you said. They are combining the CO2 with water in literally like a soda stream, and drill a hole in the basalt and inject that soda carbonated water into the rock. And that CO2 rich water is very acidic. So it dissolves the basalt, and the basalt is very porous and young and fresh, which is great because it dissolves very quickly and the water can flow through it and percolate around. And then when the basalt dissolves, it releases calcium and magnesium and iron, and then converts the CO2 from being carbonated water gas into bicarbonate, alkalinity, what it's called in chemistry space. And then eventually the solution becomes what we call supersaturated, meaning there's so much dissolved stuff that the water wants to do something with all that dissolved stuff. And so that's when the carbonate minerals then precipitate. They grow out of the water because there's so much calcium and carbon in the water that they need to combine, and they like to form a carbonate mineral. So that the CarbFix method is essentially doing exactly what nature does over million-year timescales. It takes CO2 and water, converts the CO2 then into dissolved form, reacts it with the rock to further dissolve the CO2 into bicarbonate, and then that combines with calcium to make carbonate mineral, which is, again, what the entire long-term carbon cycle does over million-year timescales naturally, except at CarbFix, because you're doing it underground and basically like a more dense, concentrated reactor, for lack of a better word. They can mineralize carbon in only 2 years.
That's beautiful. Now, this is your favorite method, right? That's the thing you like to promote, right? Now, what I'm not clear about is how you capture the carbon in the first place for this, how that outfit captures the carbon, which it squirts into the water like my soda thing, and so on. Isn't there a lot of energy required to do this carbon capturing?
Yes. So the in situ mineralization is essentially a storage mechanism, a geologic storage. That method that I just described doesn't have anything to do with capture, which you're exactly right. It relies on CO2 being supplied from somewhere.
And there's an outfit called Climeworks that is based, they have an operation in Iceland. Is that where they get their CO2 from Climeworks?
That's one of the places, yes. So the initial project, the pilot first trials of injection, they got their carbon from the geothermal power plant. So it was what we call a point source, so an emission source. So they just capped the CO2 coming out of the power plant and tested out the whole method using that. But
no, wait a minute. This power plant, what Iceland has a lot of geothermal stuff. So this was not a regular geothermal power plant. But
yeah, it was.
It was.
It
so
was.
Why is it emitting CO2?
Geothermal energy does have CO2 emissions because you're bringing up gases from a hydrothermal system. And there's carbon dioxide gas coming out of a volcano that is Iceland. So even though the emissions are much, much less than a fossil fuel energy plant, for example, there still is like some amount of emissions. So they used that CO2 in the first pilot test. But then you're right, they did partner eventually with a direct air capture company called Climeworks to basically demonstrate that you can do this with CO2 capture directly from the air. And a couple of reasons that is beneficial to demonstrate is that the Orca plant in Iceland, which is the partnership between CarbFix and Climeworks, is a prime example of a negative emissions technology that has the potential to remove legacy carbon. So that we can have plants like those and still work tirelessly to get to a zero carbon economy and society, not just a net zero, but actually stop emitting carbon and decarbonize our global society. What we would still need a certain amount of plants like that plant to remove the legacy carbon. But you can also use carbon captured from point sources and inject and store it in basalt. So the other plant in the Pacific Northwest, the Wallula Basalt Pilot Project, used a different form of CO2. They used liquid CO2. So that CO2 was captured elsewhere and compressed, which also takes energy, but not as much as direct air capture. And if you have a compressed tank of liquid CO2, it's much easier to transport than have a gas, for example, less leakage and less risk.
Where did they originally get their CO2?
I'm not entirely sure.
I'm being suspicious because I want to make sure that that there's an economy there that makes any sense, that you're not using more energy to get the CO2 than you're actually going to get the value from. So, that's why I'm asking you where they get this CO2 and how much energy did it cost them to get it?
Yeah, I don't know. That is a good question that I'm not quite sure of the answer of, but yeah, I have a lot of thoughts on like point source versus direct air capture, because in general, I mean, unless you're trucking CO2 or bringing it on a train or whatever from across the world, it's probably not as energy intensive and expensive as direct air capture, but Don't quote me on that. I'm not positive, but I know that in Iceland, they are looking into bringing in CO2 from point sources in Europe, which is great, I think, even though there is a downside of, that we still want to work towards stopping emitting. But
I would think that even in Europe, there would be places where you could hide the stuff. There's basalt someplace in Europe close to where you get your CO2, so you could put it. Is there a scarcity of places where you can put the stuff, the basalt, in caverns or whatever?
Not exactly, but it is. So I guess I'll rewind and mention some of the downsides of the CarbFix method. And basically in Iceland, it's just the perfect place for this because the rock is very young and reactive and porous, and there's tons of fresh water, and there's also renewable energy. So you need the specific rock type, obviously, which continental flood basalts, like for example, the Pacific Northwest or the Deccan Traps in India, are generally not as reactive and porous as what's called mid-ocean ridge basalt, so like the one in Iceland, or even Hawaii. It's younger and more active. So it's kind of better rock type, but the major thing, in my opinion, is the water. So the method in Iceland, you need about 25 times as much water as you do CO2. So because you're dissolving it in that soda stream situation, you need about 25 tons of water per ton of CO2. So it's extremely water intensive. So, which isn't a problem in Iceland, but in other places that is.
Compared to other places, 25 is good or bad, I'm not sure.
It's a lot. You need, for every ton of CO2 that you mineralize, you need 25 tons of water. That's a lot.
And other places you might not need that much water.
Yeah, well, so that's kind of what I'm going to work on at Columbia, is trying to move this offshore. So in order to scale up to a point where we're making a much bigger difference in terms of climate change mitigation, we need to scale up like drastically. So the plant in Iceland removes 4,000 tons of carbon per year. In order to get to we basically need to scale that so that we need plants that will remove that much as the Orca plant removes in 1 year in like 10 minutes. So we need to get to a point where we're scaling up massively. So 4,000 tons a year compared to 50 billion tons that we emit. So we need to scale up hugely. And in order to scale up, we need to move offshore because the entire ocean floor is basalt. We need to
also you've got plenty of water in the ocean, but is it that you have to have fresh water? It doesn't work with salt water?
We haven't, CarbFix's Project Seastone is testing it with seawater. It has been demonstrated to work in laboratory experiments with seawater, but we need to test it with a pilot demonstration using seawater, and also in basalt offshore, because when you're underwater, the rock chemistry is a little bit different, temperatures are a little lower, pressures are a little different. So we need to move the operation offshore. And we also need to not only demonstrate that it works with seawater, move to an actual offshore setting, but we need to experiment with different types of CO2 injected. So instead of dissolving it in water and injecting soda water, I'm interested in figuring out, okay, well, what happens if we just inject pure CO2? Kind of like what they did in the Pacific Northwest. They injected pure liquid CO2, no water. And that's what we really need to do to get to the gigaton scale, is just liquid CO2. Because otherwise you're clogging up all the pore space with tons of water. And but if you're not injecting water and you're just injecting CO2, the reactivity of the basalt changes and the chemistry of the subsurface changes. So those are the types of questions that we can answer with reactive transport modeling and with computer modeling. is calculating, okay, so if I inject this much CO2 into this size and shape and type of reservoir, what reactions are going to occur when? And
And here's the kind of question that occurs to me. I just read something yesterday about all of the different ways that they can use CO2 to make things that are useful. And so my question is, without going into all of these different ways of combining CO2 to make things that we can use, why would you want to waste it? I mean, if you got all this CO2 and you can do something with it, why would you want to put it in the ground and forget about it? And the second part of my question is, does this have anything to do with the way they are going to be making concrete? That, as I understand it, there's a way of capturing CO2 and combining with either with something else and crushed stone or with old concrete that you've mashed up and to recycle, etc., and make limestone aggregate, which then can become the ingredient for new concrete. Now, is this chemically related to what goes on in the ground when you shoot your CO2 down there?
I'm glad you brought that up because I have a lot of thoughts that I've been recently working through about utilization. But yes, to answer the question in short is, yes, it's a similar reaction. You're mineralizing CO2, creating calcite or limestone, and that works in cement as a kind of aggregate. And there's a company called Carbon Cure, which I'm sure you're maybe familiar with, and they do this. They're out of Canada, and they have you can make potentially carbon neutral or even carbon negative cement. So the cement and concrete industry is a massive emitter of CO2 right now because you burn limestone and produce CO2 in order to create cement, but there's ways being researched to essentially recycle that CO2 that you burn off back into the cement. So that would be carbon neutral. Or even there's ways being researched where it's carbon negative, where you consume extra CO2 during the process. And I'm not that familiar with that, other than it is kind of the same mineralization, calcium carbonate chemical reaction. But back to your first question about utilization is, why would you store it when you could use it? So this kind of goes back to that initial like mass balance of carbon in the atmosphere. So we need to get to a net negative, not just net zero society in order to curb global warming by 1.5 degrees C. So utilization in general results in net zero, if at all. So if you're recycling carbon that you, for example, Climeworks, the Swiss company, they started out by using their CO2 that they removed from the atmosphere and selling it to greenhouses or to even, I think, Coca-Cola to make money, because direct air capture and a lot of these capture technologies are so expensive. They're not scaled to a point to drive the price down, and they need to sell the CO2 in order to be a viable business. So utilization is an important piece to help us scale capture technologies because it helps with the economics. But it's also, in my opinion, a little bit of a slippery slope, because if the utilization economy probably will explode such that like a lot of companies and businesses will say like, instead of buying CO2 from a commercial source or from an industrial process that involves burning methane or whatever, they'll buy captured CO2 and say like, we're carbon neutral this, we're carbon neutral that, which is good because it is mitigating more emissions. However, we're only going to get to a net negative or a carbon negative to the point where we're removing that legacy carbon if there's also a incentive to just geologically store CO2 that's captured. If a lot of utilization companies start popping up, then why would the government or companies pay to just store their CO2 if they could
to make it worthwhile? It's really, somebody's just got to pay you to do it. You're not going to get any value from it. I mean, nobody can make any money from putting in the ground, but
Exactly.
you could make money from other things as long as you could use all of this. But you can't use all of the stuff that you're going to capture. You got to capture more than you can use. Is that the general problem? So you have to be ready to throw it away.
Well, I think the problem is that the demand for using CO2, like there's already an existing demand for CO2. It's used in a bunch of different industries, for a bunch of different reasons. So like as the consumer and our kind of market shifts towards people wanting to see net neutral or net zero or whatever, carbon neutral on everything they purchase, people are going to have an incentive to use captured carbon versus industrially produced carbon, which has the benefit that it will help carbon capture companies scale because they'll have revenue stream, and B, it will mitigate the emissions that are associated with the original carbon production industry. So it'll be worth it for a company that uses CO2 to buy the more expensive captured from the atmosphere CO2 versus the cheaper industrially produced CO2, because then they will be able to say that they're net neutral, which has a value associated with it. But so the downside, in my opinion, is that none of that, that does help with one aspect of climate change mitigation, because you're lowering emissions or preventing emissions, but you're not actually capturing and removing carbon. So it doesn't really that, it gets a little murky, the carbon capture removal industries, because if you can get a carbon removal credit by just using captured carbon and not using emitted carbon, there is no actually net negative. There is no carbon negative. That's just neutral. That's just not emitting. So then if the market becomes that you are incentivized and can sell a carbon credit by doing that, then who's going to pay extra for a carbon credit to do the actual storing piece? So I don't know. It's confusing but right now, you can sell an offset by just preventing emissions, which in my opinion isn't good enough. Offsets should be that you're actually consuming and permanently storing, not just not emitting. Does that make sense?
Yes, it makes sense. It makes sense. There's a lot of concrete being used in the world. That would be wonderful if we could make all the concrete carbon negative. We could, I don't know how many gigatons we get, but it'd be great. Okay, our time's up. And this has been just glorious. I've learned so much, and I'll think about it further, because now I've got new things to worry about. And you've given me more grist for my mill. Thank you very, very much. And I certainly hope you have a huge success with the work you're doing, because it's going to save the world, and you're doing it. So thank you.
Thank you so much for having me. This has been a pleasure. Thank you.
Okay, bye, Claire.
Bye.
These conversations are produced by Project Save the World, which maintains a splendid website as a meeting place for activists who are addressing the threats facing our planet and humankind. Please visit it at tosavetheworld.ca. You can search there for this episode by just entering the episode number 382 in the search bar, or the title of the show, How to Turn Air into Rock, or Claire Nelson's name. You can also access the audio podcast there, and eventually the transcript, and then scroll down and share your own thoughts about the issues that we've discussed here.